Thank you. Right, last time we were going through examples of semaphores. Today we're going to continue along this trend and start to show some of the problems when using them. I thought it's good just to remind you of semaphores at a higher level. So this is looking back at the previous thing where we talked about a process states, where you either have executing, blocked, or ready. Um, so how does this state diagram change with semaphores? Well, OS time delay, this is sending from executing to blocks. This is as before. As before, then we could have a timer interrupt. So this is 2. So an ISR. To take you to the ready queue, and then to go to the ready queue to execute, you have the operating system picking the highest priority task and scheduling it. So just how does this change with semaphores? Well, semaphore, you're going to have something that's executing, some process or task that's executing, and then within the task it's going to call OS_sempend, which is saying wait until a semaphore is available. If it doesn't have it, then it's going to go to the blocked queue. And it's going to stay there indefinitely until some second process which is executing is going to put an OSM post. Now that OSM post, it's going to take something, it's going to potentially push the first task from the blocked queue to the ready queue. So this will be OSM post. So it's in the ready queue. Does it go straight to the executing? No, it requires the scheduler. So like we've talked about before, what might happen is the scheduler at some time unit will preempt a task that's executing the one that did the post, and then it may choose to schedule the task which was previously waiting on the semaphore. Now, no, because when we're using semaphores, things only go to the ready queue. They don't go straight to the CPU once they get the semaphore. It just means that you can't expect instant action, right? We're still depending on the operating system to choose highest priority task. It just defines what tasks are currently available to run. So we talked a bit about semaphores to protect variables, protect global shared variables last time. Today we're going to talk also a bit about how we can use it to pass a message. So, all right. To pass a message using a semaphore, the idea is that, well, if this guy says pend on a semaphore, then, and this guy wants to pass the message, if this guy says the post, then this guy can start running. So we send a message post that allows me to start running. Similarly, you could write to a place of memory, hit the post operation, and say the data is now ready. Right, that's a very high-level view. It's probably easier by examples. So we've got a heap today. Right, first one is going to be a bit unrelated, actually. First one is regarding the timer. So if you remember that when we initialized the semaphore, we have 3 criteria that we can initialize, which are, I've previously mentioned, right, sorry. when you're waiting on a semaphore, you have the option to take OSM pend, and I've only talked about giving the name of the semaphore and nothing else. I've said wait on a given semaphore. You have the extra options of you can pend for a given timeout, which will be a given number of clock ticks. Depending on if you time out or not, then it will return an error message whether you've timed out or not. So this task is to demonstrate this and also to get some people to speak to me from the audience. So, what do we do in this task? As before, we start off with start task, which generates all our tasks. What does it do? It starts off by creating a semaphore with a value of 0. Then creates a task, and we're going to start off with version 1. In version 1, so it creates a task, then it's going to post the value of a semaphore. Okay? Then start task does nothing but finish. The other task, which start task creates, it waits for a semaphore and prints that once it's got the semaphore, I receive the semaphore. So this task is just extremely straightforward, and you should all be able to imagine what happens. The start task is going to create a task, it's going to post a semaphore, the other task is going to wake up, check if the semaphore is there, oh wait, it is already there, it's going to run and receive it and continue. So, while that's working, we can start chatting about the next task. Right. So, creates a task, says, post the semaphore. Do I receive the semaphore? Yes, I do. Okay. I hope you're all thrilled by this example. In version 2, we have basically the same code, just have a slight complexity, is that we now have a delay before we post the semaphore. So in version 2, we have a delay of version -1. So we have a delay of 1 clock tick before we post the semaphore. So anyone, what do you expect to happen? Start task starts, then it goes to sleep. Task 1 starts, waits on the semaphore. Will my output be any different to what it was previously? Nodding. He's nodding. Why are you nodding? It feels like you should. It's got to be different. No. Oh. Yeah, it's going to be exactly the same as before, basically, because we're going to, the task is going to wake up, it's going to say, I'm waiting on the semaphore. Now note, it's going to be slightly different because we go to sleep before we post the semaphore, then there's going to be a slight reordering of the text, right? You're going to say, I'm waiting for it to be posted, then the start task is going to say posted, and then you're going to say, okay, I've received it. It's just going to have a slight reordering of text, but that's just playing with priorities. Okay, so that's all trivial. What happens if I change it to be version 3, and now I have a delay of 2 clock ticks? I will get an error. We have a vote for an error. Yes. Does everyone agree that we will get an error? Does anyone disagree that we'll get an error? Can you suggest why you would get an error? So I put 2 as my timeout. Right. So I time out after 2 ticks. Does everyone agree that I'll get an error? Yes? No? Yes, everyone agrees. We got no timeout. We got no error. No. Right. 1 minute, discuss with the people outside you. I'm going to pick someone random from the crowd. Completely random. Alright, everyone, with the person next to you, I'm going to pick, and you have to have a spokesman. The person who is oldest in the 2 or 3 around you has to answer the question. So, we did not get an error. Why? Okay, 2 minutes is up. Random person to answer. This group here. You 3 guys. You 3 guys, the one who's turning around nervously. Do we have an answer? We have no clue. Oh. Is there any group that can volunteer my answer? We've got an answer. Okay, so this is close to the correct answer, but not quite the correct answer. It's just a question of priorities, this, right? So, start task is delaying for 2 ticks, right, before posting. Task 1 is delaying for 2 ticks before it gives up. So, start task delays for 2 ticks, then both wake up at this point in time. Which one runs? The higher priority is start task. So start task runs, what does it do? It posts. Okay, it continues to run, and then it has a time delay. Okay, so now task 1 starts running. Task 1, it's woken up and it goes, is the semaphore there? And it goes, yes it is there. Right? So it's just had enough time. If you have a little bit more time, so giving you an extra clock tick delay, I think we could all guess what happens here. Error message, yes. So, what happens if I were to have a delay of 2 ticks but I reverse the priorities. Would I get an error message or not? Quick vote. Error message. No error message. Half the class are wimps, half the class are right. Right. I will get you all to partake by the end of this session. Okay. Next example. Our next example consists of a simple producer and consumer task. Right. So what happens in this? Our start task initializes semaphores for producing and consuming. So it says one, you're producing at 0, you're consumed to 1. Right. Then it produces a producer task, a consumer task, and then just waits for the tasks to do their stuff and complete this demo. Right, so what does the producer task do? The producer task waits on a semaphore on whether you've got one consumed. Right. And then it posts, it creates an item and then posts that I've created an item. The consumer, it waits until you've produced an item and posts when you consume an item. So one goes up, one goes down. You got a producer adding items, a consumer taking them away. It only takes them away if they exist. It only produces if they're needed. Okay, so I've got a few versions. My consumer has higher priority to my producer. What's going to happen? What should happen? Well, so my consumer is higher priority than my producer, but my consumer cannot work until there are items available. So you'd imagine that we're going to be producing items and then consuming them after. While we're doing that, you can think about what happens if I swap my priorities around. So yes, I produce an item, I consume it. I produce an item, I consume it. I hope you all can read that. This is just, the numbers is just how many items I produced so far. So it's just straight, lockstep, produce, consume, produce, consume. So what happens if I swap the priorities? The consumer will it still has the same relationship that it can't produce until it's consumed. Because all I'm doing is waiting on one item to be passed. So are we expecting any difference? There's actually no difference at all, right? The priorities don't matter because one can't do anything until the other's ready. And once it's produced an item, it sends the message across, I've produced it. So the consumer wakes up and goes, okay, you produce an item, I'm taking it. Then it says there's no items left, and then the producer goes, okay, I'm going to make another item. So whatever priority it is, the semaphore is actually defining the order of operations, not the priorities in this case. Okay, so that's all well and good. Let's look at a slightly more interesting example, which is where you have, instead of a single item in your buffer, you want multiple items in your buffer. So you can produce however many you want, up to some limit. Right. So, walking through the code, what we have a buffer of size 5. So we can store up to 5 items. We've got some global variables which store the number of items we've currently got and some index to the buffers. So we're going to read and write. So you can imagine you've got this circular buffer. We're putting in items throughout it and consuming them at a different rate. Okay, so that's the idea. How does the code look? So to store an item, I say, do I have any empty places? First, so is there spare room in my buffer? Then I say, okay, my buffer is a shared global variable, so I'm going to protect it. And then I'm going to add an item to the buffer. Once I've done that, then I'm going to signal to my other process that I've added a new item. So you can go consume it. Okay. While we're here, quick questions. How should I initialize my semaphore? What value should I initialize the number of empty places to be? Yeah. So if you set the number of empty places to 5, then this code can enter 5 times, produce 5 items, and then it's going to have to wait for the consumer to take away those items. How should I initialize my protection, my memory? My memory protection semaphore, so that only one thing can access it at a time. What value should I give it? 1, yes, 1. And how about the number of places? What should I initialize this to be? So the number of items that are currently in the buffer at the beginning of time. Straightforward, yes? Not hard questions. Right. The retrieve thing does basically the same thing. Wait until you have something in the buffer. When you have something in the buffer, ensure that you're the only one who has access to it, and then once you've taken away the item, say there's an extra space available. So you can see how these tasks interact. And yes, so in our initializations, we have a value of 1 for protect the shared memory. We have 0 to say there's 0 places in the buffer at the start. And we have 5 places available to fill up in the buffer. Okay. My producer task, what it does is it simply says up to 10, print out while I produce a task, and then go and produce something, which is the code that we've just talked through. The consumer task basically does the same thing. It says, just runs the code, consume an item. Okay, now come the games. The consumer works slower than the producer, but the consumer has higher priority than the producer in version 1. So, will the buffer fill up first, or will it fill up and then just take one item at a time and replace it? Or will it work the other way, just have one item and it's instantly consumed? We've got several votes for one item instantly consumed. And you can see here, we produce, then we consume, and then we produce 5 items. Then we produce and consume, then produce and consume. So actually what's happening is we're filling up the buffer first. Right. So this is not really what was predicted. Why is that? Yeah, so the key here is not priorities, it's the fact that you've got something slower. So you could imagine that you've got people putting things on a shelf really quickly, and one guy just taking a block and having a beer in between and stuff. You can imagine very quickly what's going to be the situation. Version 2, producer works slower than the consumer. In this case, what's going to happen? So in this case, it's the same situation you should be able to envisage. Okay, so producer works slower than consumer. So producer has his beer, puts the thing on the rack. The consumer then takes it away instantly. So you can imagine that we're going to have the opposite situation where we're just having this, second it's produced, it's consumed. Okay. And this is what happens. We produce an item, we consume it. We produce, we consume. Just so, how do we ensure that one works harder than the other? Well, we've just done this using delays. So, in version 2, I have a time delay of half a second with the producer and nothing with the consumer. So the consumer instantly takes it away. So you can easily implement delays just by using time delays. And you can also implement delays by simulating that the processor does nothing, just by writing a for loop that runs forever. Okay, carrying on. Version 4. Let's just go to version 4 because version 3 is rather similar to the previous one. You can feel free to go through it in your own time. So version 4, I haven't actually talked about it. Right, so in version 4, we create our 2 tasks, as you see, and then for some unknown reason, nothing happens. We don't produce, we don't consume. Right, it looks like our operating system has crashed. And interestingly, well, start task should say terminating after 5 seconds, but you notice that still nothing's happening. So my operating system has crashed. Has it crashed? It's actually working very hard to do something that's very difficult. Which we'll talk about in a second. What it's reached is so-called deadlock. So let's talk about that now. So the idea of deadlock is that you basically have 2 processes waiting on each other. So you could call it, here it's called a deadly embrace. So task 1 holds one vital resource, task 2 holds the second vital resource. Task 1 needs task 2's resource, task 2 needs task 1's resource. No solution to the problem. No, unless someone times out and gives it back. Right? And this is basically your most common problem with semaphores. Okay, simple example of how it can occur. Task 1, it waits on a semaphore. Task 2 waits on a semaphore. Okay, let's suppose task 1 gets it. It goes through its critical section of code. Okay, now what happens? Task 2 wakes up. Task 2 still has to wait for this semaphore. Task 1 finishes. Right? Now what happens? After a process finishes, what happens? It gives up the semaphore. It should give up the semaphore, but as you can see, this guy unfortunately forgot to give up the semaphore. So it's finished. So task 2 is waiting indefinitely, but there's something else that happens as well. What's it? Yes, processes run forever. So task 1 goes to the stop, and now task 1 is waiting indefinitely. Both places are waiting indefinitely. We've got a deadlock. Now, you might think, who would ever make that silly mistake? Second, you put an if statement. Watch out for that. You'll have an if statement. One path you'll release a semaphore, the other path you won't release the semaphore. Then you'll reach this kind of deadlock position. Okay, this is a slightly more classical deadlock situation. You have task 1 and task 2. Task 1 waits for a semaphore, it gets it. Okay, then it gets preempted. So task 2 comes and it grabs semaphore 2. Then task 2 does some work. Right? Then it gets to, eventually it says, okay, now I need semaphore 1. Well, who has semaphore 1? Task 1 has semaphore 1. What's task 1 going to do? Well, it's okay, task 2 gives up the CPU because it's waiting, so it's gone to the blocked queue. Task 1 is scheduled, so it's running on the CPU. The first thing it does, it says it's waiting on semaphore 2. Now, task 2 has semaphore 2, task 1 has semaphore 1. And you've got this classical situation of no one's giving up their resource, and we're going to be blocked forever. Okay. Designing philosophers. Now, this is the classic deadlock situation. Right, so we have philosophers. Now, philosophers are very clever people, so they think a lot, and they need fuel, so they eat a lot. And these are Chinese philosophers. They need 2 chopsticks to eat, you know. Can't just get away with 1 fork, right? So you got to grab your 2 chopsticks. Right. And now, right, I want you to think for 2 minutes and tell me how this can come up with deadlock. Same process. I'm going to pick someone random, and this time they can answer it. 2 minutes. Right. Random person 2. Older one of you two.
You would end up with each philosopher grabbing one chopstick each,
Each philosopher grabs one chopstick each. So this guy grabs this chopstick, this guy grabs this chopstick, this guy grabs this chopstick, this guy grabs this chopstick. We wait forever. Right. If you want to see this in code, I've written this for you. Right. We can have you can have any given chosen number of philosophers, and we have our chopsticks, which are our shared variables. Each will be protected with a semaphore. A philosopher will either eat. His eating process consists of a loop which says, I'm eating, and then it continues to increment a variable, and then it goes to sleep for a little bit of time. It can think, and its thinking process is exactly the same. Does a bit of hard work, and then it just, you relax for a bit and take a step back. Right. The philosopher, what it does, he grabs the left chopstick, then he grabs the right chopstick. I should have it here. You wait for the left chopstick, then he says, I've got my left chopstick, then it has a bit of a think. He grabs the right chopstick, then he says, woohoo, I got my chopsticks, I can eat. I finish my food, I say, yummy. Then I return my chopstick, my right chopstick, return my left chopstick. Then I have some long period of contemplation because I'm full. Right. Now, I've initialized the semaphores for all my various chopsticks. I was lazy and just copy and pasted a lot. Then I created my philosophers. The philosopher has an index of I, and then it has a chopstick and the next chopstick. And then we go, this is modulo the number of philosophers, so this limits the amount of chopsticks that are available. Create our multiple philosophers, and then see what happens. And this is exactly what happens. We have philosopher 0 gets the left chopstick, philosopher 1 gets the next chopstick, philosopher 2 gets a chopstick. Each one of my philosopher grabs a chopstick, and then they're all waiting on someone else to release their chopstick. Right. So, now we need a solution for this problem. We could do timeouts. Timeouts is one solution. What about, right. So we always grab, in this code it timeouts straight away because we're always grabbing, everyone grabs the left chopstick first. What about if you grab, some people grab the right chopstick, some people grab the left chopstick? Is that going to solve my problem? So I've written a second philosopher task, and instead what it does is it says, I have some random variable. If I'm greater than some number, I grab the left chopstick, otherwise I grab the right chopstick. Who thinks that this is going to solve my problem? No one thinks this is going to solve my problem. One person thinks it solves my problem. Why do you think it solves my problem? one person might get to eat or think. Now, sorry, this was actually the wrong code. I have to invoke my second philosopher task. So, what can happen is one guy, if I look at my diagram, this guy randomly picks, he's going to pick the right chopstick first. This guy's going to randomly pick the left chopstick. Now he's going to have to wait on that left chopstick. Now this guy's going to come back into play, and he's going to pick my left chopstick. And now he can continue. And now this can work. As we can see, my philosophers are working forever. Who thinks this is a good solution? You think it's a good solution. He likes it. This guy doesn't. What's wrong with my solution? It's working on randomness. Yes, what if I randomly all choose the left top six first? Right. Right. Okay. That will not solve my problem. So let's just imagine a different way of solving my problem. Let's... Yeah, timeouts will work, but we want to not use timeouts. What I'm going to do for my second solution is everyone grabs the left chopstick first. However, you look at my philosophers, and we have a green philosopher, right? I hope you can all see this green philosopher. Now, he is obviously, he's green, so who's a famous green philosopher? Can anyone tell me? There's only one famous green philosopher. Yoda. This guy is Yoda. So Yoda is important, right? So Yoda always goes first, right? So we let Yoda pick up his two chopsticks and eat. And then we see what happens. So who thinks this will solve my problem? Seems to be working. There's a lot of thinking going on, but there's no deadlock here.
One of those eats, right? And then he puts it back, but then the blue one takes it, but then the red and orange, they have really
Yeah, so basically, you're right. There is still a small chance. Now, what you've done is, if this guy has taken both chopsticks, then what's going to happen is the first guy's going to wait, and then this guy's going to take both chopsticks, right? Then they're both going to all release all the chopsticks, then this guy's going to grab them and grab them. And just by chance, it's going to fit in nicely, but there is, over an indefinite period of time, with enough philosophers, you could have it so everyone picks up the left chopstick. Right, so we do need a solution to this problem. Can anyone think of a solution? Assignment hierarchy. Right, so what you do is you say, this is the first priority chopstick, this is the second priority chopstick, this is the third priority chopstick, and this is the fourth priority chopstick. Okay? And the idea is you can only grab if you have chopstick 1, then you can grab chopstick 2. If you have chopstick 2, you can grab chopstick 3. If you have chopstick 3, you can grab chopstick 4. If you have chopstick 4, you can't grab chopstick 1 because it's a lower number. So if the red guy wants to eat, he has to first grab chopstick 1, and the person who holds chopstick 1 can grab any other chopstick. So this guy who grabs chopstick 1 can grab chopstick 4. Right. And this will solve your problem. Now, I challenge you all to code this in your own time, but the key idea is you have to acquire resources in the same way. Before we finish, I do want to explain how we avoided deadlock, how we got to deadlock in my previous example. So in this multi-buffer, you remember you had a deadlock situation. Now, the reason I put it off is it's actually a bit of a subtle deadlock situation. So in version 4, I enter this critical section, and within the critical section, I run this retrieve item. And this retrieve item process, a function, calls on a semaphore. And now what we're doing is we're calling something within a critical section within a semaphore within a critical section. And this is actually messing up our order. Right. It is late. I'll go over that again next time just to make it clear.